that repetition value, which one gives maximum. Sometimes you take the random repetition factor. So then the base station is going to broadcast so here this is the number of preambles or repetition factor. This is one agent, this is preamble. So then it will repeat again for the second time slot, third time slot, fourth time slot. So like this iterative process continue. So then this Q table will be updated. So Q table starting from 0, 0, initial value is 0. So then the reward is going to be here. Reward, how many devices successfully served at the end. Divided, this is a normalization factor. So then you put this number, this is 0. Then, so here, which action give the maximum value, then put this, then you repeat again and again. So starting from time slot 1, so continue. So then this Q table will be updated starting from 0. The Q table will be updated over the time. So this is Q learning. So in the double Q learning, so here what we are going to do, so as I mentioned earlier, so here, so this part, so here, this part, this one, for this operation, we have a separate neural network. So here, you see the algorithm here. So same thing like earlier Q learning. So here what we are going to have, here two Q network. One is primary, other one is target Q network. So in the target Q network this is the target, this one. So here the same iteration is starting, so set the values here. So the memory, initialize the memory. So then for primary network, this theta is the neural network matrix, weight matrix, neural network. So every branch has weight. So then we have a weight matrix. Target matrix is theta bar, the other Q network. So then you do the same thing here. So then for every K step, so theta bar is replaced by theta. So this is the algorithm for double deep Q network here. So if you refer these papers, so step by step all the details are there. I skipped because I cannot put everything in the slide. Okay, so yesterday, so we did, so here, so what is happening here is, if you take the green line and the blue line, this is the repetition value fixed. Say here repetition value 4, here repetition value 8. It is fixed. So the red one is the machine learning based, the proposed one. So if you take the machine learning one, say you see the red one. So this one is repetition value. This random access opportunity, this means multiplication of other two parameters. They have three parameters. One is repetition value, other one number of preambles, other one how many random access opportunities. So this one is number of preambles multiplied by the allowed number of the random access attempt. That is called random access. So this is one parameter. This is the multiplication of other two parameters. You see here. So here repetition during the bursty traffic, repetition the value decreases for the machine learning one. Why repetition value decreases? If you take 640 milliseconds, if you have more repetition, then you don't have time to transmit the data. So here you have so many devices during that time peak. So 10,000 devices want to access. So if you use this number of preambles, then you don't have time for scheduling. So that's what here this reduce the repetition, increase the random access opportunity. Then only it can serve as many users possible, because during that bursty traffic, so 10,000 users try to access. For you have to allocate the time for 10,000 users. So if you want to allocate the 10,000 users, if you use a repetition factor this much, then you cannot allocate 10,000 users. So that's what here you can see repetition value decreases here. So here decreases. Here other two values increases. Here other two values increases. But if you take the load estimation approach, so what will happen? It estimates the load. So since the load is heavy, so then they reduce automatically here. So that's what they are unable to serve as many users possible during the bursty traffic. So that is the reason this reduces, this increase. This reduces, this increase. If it does not reduce it, cannot serve it. Because the repetition factor this much occupy everything. So many devices are waiting. But if you increase the repetition factor, you can't satisfy the requirement of so many users during that particular 10 seconds. So understood now? Yesterday you asked me, no? Now understood? Okay. Okay, so now if you want to clear any doubts, so you can refer this in IEEE Explorer, all are available. Okay, so now we have to predict the load, because now up to now we haven't considered random access control. Up to now we considered only the 9 parameters. We haven't controlled about the random access. Now we have to control the random access. Control the random access means if 100 people try to access, we cannot allow all, base station will not allow all 100 people at the same time. Base station will allow only 40 people it will allow. So how it will allow the 40 people? So that is access control. So now we are going to learn access control. Earlier we assumed that access control is separate. So we just consider narrowband IoT, every region 3 parameters, total 9 parameters we considered. Now we are going to consider access control. Then finally we consider access control and the 9 parameters together. So now to control the access, what we have to do, first we have to estimate the load. So load means how many users are waiting. So how we are going to estimate the load. So if you estimate the load only, say for ACB factor. ACB factor means, so the base station is going to broadcast one factor. So user devices generate a random number. Those who are above that number are allowed to transfer. So how the ACB factor base station is going to broadcast, it depends on the load. So if the load, say 500 users are trying to access, it will broadcast different factor. If 100 users, it will broadcast different factor. If it is 10 users, different factor, because 10 users all can access. So you can say number 1, anyone can transfer. If you have 1,000 users, so if it wants to allow only 100, so it will say only 10%. So that means those who above 0.9, you can transfer. Say if you have say 200 users, it wants to allow 50%. So it will say those who above 0.5 you transmit. So that factor 0.9 or 0.5 or 0.7 or 0.6 depends on the load. So therefore it has to estimate the load. So now we are going to see two things. One is estimation, other one prediction. Estimation means during the current time slot, you estimate what is the load, current time slot. Prediction is what is going to be the load in the next time slot. That is prediction. So you are going to predict the load for the next time slot. Estimation, estimate the load for the current. So there are two words. One is estimation, other one prediction. So now we have to predict. So that means during this time slot, we have to predict what is going to be the load next. So then only at the beginning of the next transmission time interval, it can broadcast the ASB factor. If it does not predict, then it can't it can't broadcast at the beginning of the next transmission time. So therefore, we have to predict, not estimate. So here if we take the literature, so here the framed aloha, so the key component in multiple access protocol, whether it is Wi-Fi or GSM or LTE or 5G, everywhere we have the framed aloha. So if you take the framed aloha, so here, say for example, say here if you take random access preamble in narrowband IoT. So here every time slots, so we have preambles. So the number of preambles are here. So every time slot, some preambles succeed, some preambles idle, not utilized, some preambles collided. There are 3 cases every time slot. So now you have 50 preambles you have. So users are going to select the preamble and transmit. Out of 50, maybe 25 succeeded. So nobody selected 10. So 10 collided. Because nobody selected 10 means every three or 4 people selected the same preamble, but some other preambles are there, but they don't know that they are free. So they say at the same time, 3-4 users select one preamble, but they don't know that there's another preamble free, idle there. So therefore, we are going to have 3 cases. So here, say up to time t, so we have the observation. So from this observation, we are going to predict, so that is going to be the load, n is the load. So how many users are going to be in the next time slot we have to predict. So if you take the normal conventional method for load prediction is load estimation. So they estimate the load and say here during the time slot t, they estimate the load. Based on that estimated, they say that next time slot also same, but that is not correct. So we estimate during this time slot, you estimate the load is 50. You can't say next time slot also 50, but existing literature says that next time slot also same. But next time slot it may be 70, it may be 80, so different. So therefore, so these existing work here, so in this literature, they use the estimator, method of moment estimator, maximum likelihood estimator are there. So based on the observation up to time t, they are going to estimate this during the time slot t, estimate this and assume that t plus 1 also same, but that is not correct. So therefore, there are 2 types of estimators in the literature. One is method of moment and maximum likelihood estimator. So here, if you take that estimators, for example, so this is in the in our paper, the communication letter paper. Where's the paper? I can show the paper. This paper. So communication letter paper, this all technical details are there. So here, say I just put what is meant by method of moment. So here, say you have load nt. So in any frame t. So if you have f is the number of preamble. If f is the number of preamble, you can calculate how many preambles are going to be idle using the probability. So if you have f preamble, the probability to select a preamble is 1 over f. The probability not to select is 1 minus 1 over f. So all preambles are not selected. So therefore, f minus 1 over f minus 1 over n times you multiply. So then expected value, so here f times this expected value. So similarly, you can calculate using the probability expected value. So once you calculated the expected value, so now you have the observation. So from here, so we are going to find the mean absolute error. So this is the expected value here. This is the expected value for n here. This is expected value for collided here. Then these are the observed value. So then we have the absolute mean error. We are going to minimize the mean error for which value of n, for which value n this function is minimum. So that is the estimator. So this is the estimator method of moment estimator, estimate the load. So similarly, you can estimate using maximum likelihood. There's a maximum likelihood estimator, it is in this paper. So now the question is, we don't need estimator because that is not accurate. So we need predictor. So motivated by this Google Translator, so we can use the same LSTM network to predict the load. So here if you take the Google Translator, it uses short-term memory, a recurrent neural network to predict. So based on the previous observations, it predicts the translator predict. So motivated by this Google Translator, so this LSTM all technical details are available in this 1997 paper. So motivated by this Google Translator, so we apply the same LSTM architecture to predict the load. So how we are going to predict the load here is, this is the, so we are going to predict, we have observation from time slot 1, time slot 2. From time slot 1 we know how many ID, how many collided, how many succeeded. We have observation 2, 3, 4. Up to this point we have observation. We are going to predict, this is the prediction of n. This n cap is the predicted value. Earlier we used n tilde, so estimator. Here this is estimator, we approximate current time slot estimator same as next time slot. So now here we have the predictor. So LSTM network. So this is the LSTM network, LSTM architecture, recurrent neural network. So if you unfold it, so here we have LSTM units. Here we have for past T node time slots. So we are going to feed the observations over the last T slots. So then the current slot, here we have a softmax function. So this function, the purpose of this function is, so here if it has a vector of k real numbers, it would convert into the probabilities. So this one gives the probability, maximum probability for a particular number. So that is the predictor. So now the question is, here we have parameters, we have to train these parameters. So that training is done using backpropagation through time algorithm we can update. So this parameters theta for LSTM network as well as for this softmax operator. So how it is updated is here. So this backpropagation through time implementation, how the parameter theta, so using the stochastic gradient method, so we are going to update such that here the loss function is going to be the cross entropy loss. Then by that way we can do the training. So now, so we check the numerical results. So how we check the numerical results? So this is the actual traffic, the black line. If you take these two approaches, method of moment, maximum likelihood, these two approaches, estimators. So estimators estimate during the current time slot and assume that that is same as next time slot. They failed. So here blue and yellow failed. Then online, the one we proposed using the LSTM structure. So that is a red one. So red one perfectly predicts the actual load. How about the offline one? So the offline one, so that is the baseline scheme. So actually the offline one is like trained network. So for online LSTM, so these offline parameters theta are fed to the offline parameters fed to the online LSTM network. So online one is the actual real network. Offline one is the predicted one earlier using the training data. So that's what offline does not perform does not predict the actual load. Online one, so the trained after we trained using offline, we give it to the online LSTM so to predict the load. So by this way, we found that it perfectly predicted. So this green line means ideal case. So that means we know the ideal load. So this LSTM network almost predicted like ideal number. So perfect predictor. So now we need predictor, then only we can have the access control. So load predictor. So if you use the LSTM network motivated by Google Translator, we can predict the load accurately. So here this green one is ideal one. Say in the current standard, they haven't implemented using this LSTM. They use the normal maximum likelihood or method of moment. Sorry? Yeah, so maybe the next one, the current 6G standard, they will propose machine learning approach, but the current standard 5G not machine learning approach.
So the AC factor that is the side device in the
ACB factor. Yeah, so here once we predicted the load, so we need ACB factor is going to be once you predicted one, so ACB factor, so to control the access class barring, ACB factor is going to be minimum of 1 or R over NT plus 1. So this is the number of preambles available. This is the load. So which one is going to be the access class barring? So base station to broadcast access class the ACB factor, it should predict the load. So say now the time slot is, for example, time slot is 10. So at the beginning of the level time slot, base station broadcast the ACB factor. To broadcast the base ACB factor, it has to predict the load at the level time slot. So at the 10th time slot, it will have to predict what is going to be the load in the 11th time slot. Then only at the beginning of the 11th time slot, it can broadcast the ACB factor. So that's what the prediction of the load is essential, not the estimator of the load. If you use the estimator of the load, so here estimation is wrong. See, you see. So here you see estimation, blue and yellow. Blue and yellow estimation is wrong. If estimation is wrong, then ACB factor is wrong. ACB factor is wrong means collision will occur. So therefore, we have to predict the load accurately. Predict the load means every time slot you are going to predict the load of next time slot. If you predict the load next time slot, at the beginning of the next time slot you can broadcast the ACB factor. So therefore, so we need load predictor, not the estimator. Okay, so now in this work we did the load predictor. Now we are going to see the access control scheme. So one access control scheme is, that is baseline. So that means when there is a packet in the device, in the buffer, we are going to send. So no control, access control. That is the baseline. But that is not practical. In practically, we are going to have three schemes. One is ACB. So that means it is going to broadcast, base station is going to broadcast ACB factor. That ACB factor, once it broadcasts, so each IoT device will generate a random number. So every device will generate random number between 0 to 1. So base station broadcasts the factor. So they check our number is below that one, then I am allowed to transmit. If my number is above the broadcast factor, I am not allowed to transmit. So by that way, we can control the number of users access the preambles. By that way, we can reduce the collision. Say when you have 1,000 users, if you allow all 1,000, then collision will occur. So it is going to control. To control, so we have to predict the load. So if you predict the load, so then ACB factor is going to be this one. So here the number of preambles available are, this is the load. So here which one is minimum? So here the preamble, say you have 100. Here load is predicted 1,000. So 100 over 1,000.1. So it will broadcast 0.1. So that means 10% will be allowed to transmit. So if it is 0.1, so those who generated less than 0.1, you are allowed to transmit. So that means by that way it limits 100 people to transmit. Sorry, load. If the base station will estimate the load. Once estimated the load here, predict the load. Yeah, if predict the load, then it can base station broadcast ACB factor at the beginning of each transmission time slot. So now another scheme is backoff factor. So backoff factor is, so here, so this is backoff factor, this is used in the Wi-Fi. So if collision occur now, so you will have to wait certain number of slots. So that is the backoff factor. So if the traffic is heavy, backoff factor is high. So if collision occur, you will have to wait 10 time slots. Other one is here the distributed queuing. There are two parameters here. So in this scheme, only one parameter it will have to broadcast. One is ACB factor, here backoff factor. Here we have two parameters. One is the degree, other one is the depth. So two parameters. So here 3 branches. So it goes to the depth of 3. So then here total 13 frames will come. If you have 3 depth 3, so 3 squared 9. So here 9, 3. So here 1. So total 13 frames. So here if you have this, so first frame allowed, then so here it will go to this end. So here starting, say here degree 3, so he start with 3. So from 3 the arrow towards this one, because this arrow for 2, this arrow for 1, 3 here. Then cyclic 1, 2, 3 cyclic. So here 1. So the frame 4, from 1 it goes to frame 12. Then from 1 here 2. So by that way it will proceed. So here we have it is allowed first time slot, first frame. If it fails, it will allow 4th time slot. If it fails again, it will have to wait for 11. So by this way, 2 factors will be decided. So now the question is, so here just access control. So access control, so you are going to the base node, the base station E node B is the base station. So the objective is to maximize the number of devices served successfully. So here the long-term reward. So this factor consider the low weight for the future reward. Based on the observation, it is going to select the action such that so it will be maximized. So now the question is, if you use the reinforcement learning, not the load prediction. So you just use the reinforcement learning as we did earlier. Earlier we did reinforcement learning, 9 agents we had. Earlier we had 9 agents. So here if you use ACB factor, only one agent. That agent decides the ACB factor. So if you use the back-off scheme, that agent will select only back-off factor. If you use distributed queuing, 2 agents select degree and depth. So earlier we had 9 agents, exactly similar principles. We can use the deep queue learning for reinforcement learning. We can do this one-step control. Because this is easy because you are going to have only one agent. But the problem here is, if you use one agent, we have different types of agents, the reinforcement learning algorithm in the literature. So here we use DQN algorithm. There are many algorithms in reinforcement learning, actor-critic, deep deterministic, policy gradient. There are many algorithms for reinforcement learning. So we can try which algorithm performs for which scheme we can try. So few algorithms available for reinforcement learning. So we can try the DQN that we learned earlier for distributed queuing. Here 2 agents. Here back of 1 agent. Here 1 agent. Here we can use different agents we can try. So then we can do one step, adjust the parameters. The base station is going to have one DQN agent for these ACB factor or back-off factor or distributed queuing 2 factors. Now the question is, say here for when you increase the number of devices, so then when we use the reinforcement learning, so these 3 schemes, reinforcement learning, so average success is here. So if you fixed the ACB factor, when the load increases, it will fail. Say for example, say you fixed ACB factor 0.5. Up to 100 device, 0.5 is fine. So say up to 200, 0.5, say now you have 200 devices. ACB factor 0.5. So if you have 100 devices, perfect. But if it is 700 devices, if you fix to 0.5, it will fail. Obviously it will fail. So that's what here, when you increase the number of devices with the fixed value of this ACB factor or back-off factor or distributed queuing, it failed when you increase the load. It is obvious. But here the reinforcement learning approach, so the performance is better than the fixed value.
Understand one thing. Devices are increasing.
If the number of devices increases, preamble fixed.
How can the average success access it?
Say here, for example, for the first part. So here you have 200 users. So then here when you change to 250, so here we have enough number of preambles we have.
Successful access is always highest with this number of devices. Should be, I mean, that is what I believe. Or at least it should remain, I mean, so at least constant in the first part, so that we are managing higher number of devices with our algorithms, our access control schemes, and
I understand your question. What are the parameters we selected? So yeah. I agree with you. Below is fine. Why this one is increases with the number of devices? I had to check the parameters. Yeah, because your question is correct. Because when you have a less number of devices, success should be high. What would be the reason? I think I had to check the parameters because I think we changed the number of preambles. I think preambles. I can check the paper and let you know. But the conclusion is the fixed one failed when the number of users increases. The reason for this one, I can check the parameter. I can check the paper.
The second part is understood.
Yeah. So now the question is, if you have reinforcement learning agent, the problem is the convergence, slow convergence. Sometimes it may be unstable. The reinforcement learning agent, it may not converge. So that is the problem here. That is a disadvantage here. Advantage here, just you have one agent, so it dynamically change the PCB factor. It is fine. So the disadvantage is it may not converge. So then it may not be stable. That's a disadvantage. Because of that, what we did, so here we have two steps. One is the predictor, so the predicted traffic. So once we predict the traffic, then we can find the ACB factor and we can broadcast. So instead of using the reinforcement learning, if we predict the load, so if we can accurately predict, then we can accurately calculate the ACB factor. So by that way, we can solve the problem of here. This problem we can solve it. So what we did when we used our previous work, the LSTM based the load predictor. The predictor one is used to find the ACB factor or backhoe factor. So then we have the observation. So then the predicted value and from the observation we find the error. So then we feed that back to minimize the error. Say here this one predict the load. So then we broadcast. At the beginning of the time slot it will broadcast. At the end of the time slot we know the actual value, what is the actual value. So then we know what is the error. So that error the loss function will use to adjust the weight to improve the performance for the future time slots. So now, so here what we did, so here, so we predict this one, say here. So then we have the reinforcement learning agents here we have. So that means this predicted value is used as the initial value for the reinforcement learning agent. So earlier we haven't used the reinforcement learning agent. So just predictor, then it calculates the ACB factor. Now what we do, so the predicted value we use as the initial value for the reinforcement learning agent, so such that we can improve the performance further. So that means, so here we are going to have several factors we are going to consider in the reward. So reinforcement learning, earlier we haven't considered delay or energy consumption, we haven't considered. So now, earlier we considered only the reward is the successfully served devices. We haven't considered delay. We haven't considered energy consumption. So that means, say, if we repeat again and again and again, energy will be consumed every time when you attempt. So we have to minimize the energy consumption. At the same time, we have to minimize the delay. At the same time, we have to maximize the throughput. So these three objectives should be addressed. So the reward function earlier only one, this one. So maximize the number of devices served. So now we are going to have weighted reward function, because if you take the energy consumption, if you take one IoT device, so energy consumption, two cases. One is to receive the broadcast signal. So IoT base station broadcast, so it will use certain amount of energy to receive the broadcast. So that is one type of energy. Another type of energy for random access. So here we earlier we learned, so the four functions we learned earlier. So this one, sorry. So here this is the procedure, random access full procedure. So energy will be consumed for this one, this one, this one, this one. For all four procedures, energy will be consumed. So we can calculate that energy So we can calculate the energy for the first, the constants for the four steps, each step. So this is the energy consumption for random access. So this is the total energy consumed by the IoT device. So now what we are going to do, this is the hybrid, the reward function. So here we have weight. So this is the number of successfully served device or throughput here. This is to have to minimize the delay. We have to minimize the energy consumption. So here we have three sub rewards. So we have weight here. So we give priority for this one, the weight, this and this. We can choose different value. Whether we give priority for this one, then high weight for this. If we give the priority for the delay, then high weight for XD. Then priority for energy consumption, then this weight is we give priority. So now, so here the reward for the first reward, first sub reward is proportional to the throughput. Second reward inversely proportional. So that means if it consumes more energy, less reward. So if the delay is too high, less reward. So that means we have to reduce the delay. So then for these two functions, so inversely proportional functions, we can use the hyperbolic tangent function such that, because when this one increases, this one decreases, because hyperbolic tangent function between 0 to 1. So by having this function, we can have the relationship between 0 to 1 when the energy consumption high, reward less. So if we use this, the weighted reward, So here we have the predicted one. So here we have the reward function for the reinforcement learning agents. So the hybrid reward. So then we found that, so these are the parameters in the 3GPP standard. So in the 3GPP standard, so this time value, these are given. The power value for each one is 0.0 watt, 9 watts, this power 0.545. All are from experiment in the 3GPP report. So now we found that energy consumption. So when we take the ACB scheme, energy consumption higher. Back-off scheme and distributed queuing almost same. So this hybrid scheme, what is meant by hybrid scheme is, so now one device try ACB, failed. So immediately it will try other back-off scheme. That also failed. Then it will go to distributed queuing. So that is hybrid scheme. So without waiting only one scheme, all three schemes, if one fails, then try other one, another one. So that by that way, but it can quickly establish the connection. So then, so it does not need to repeat again and again. If it use only one access scheme, so it will have to try that one again and again and again, more energy will be consumed. But if it failed one, then it can try the other one. So then in the second attempt, it quickly establishes the connection, no need to third or fourth attempt. So by that way, hybrid scheme, average consumption of energy is lower. Then we learn about the reward. So here we consider the weight factor 211 we considered. So we can select some other value. So what we found that when we decouple the load prediction and the reinforcement learning for the dynamically change the parameters, we found that so the convergence 10 times faster than the other scheme. Say here, this one is ideal. So that means ideally predicted the load. So ideal one is the top one. So this is the one that when we decouple and predict the load using the LSTM and dynamically change the parameters using reinforcement learning. The other two without predicting. So they don't have predictor, just reinforcement learning using neural network or gated recurrent unit recurrent neural network. So whatever other schemes failed. So from this, the conclusion is when we have to consider three sub rewards: minimization of energy, minimization of delay, and maximization of throughput. So we have to decouple and we have to predict the load as an initialization that performs better. So now, so here, some throughput. So that means for all devices. Yeah. The some throughput or some data rate. Yeah. Yeah. So now we see earlier we considered only 9 parameters. Now in the hybrid we have 4 parameters. So now we consider all 13 parameters now. So earlier yesterday lectures we considered only the 9 parameters. We haven't considered access control, we haven't considered. Today by predicting the load we considered the access control, 4 parameters. Where? That is yesterday we considered. Yesterday we haven't considered access control. Yeah, that 3 into 3, 9. Yesterday we considered. In the random access, we haven't considered those three factors. We just considered the estimate the load. That is yesterday. Here today we haven't LSTM. We haven't here we haven't considered only the ACB factor, backoff factor, distributed gain 2 factors. Only these 4 we considered. I haven't considered here narrowband IoT. Standard I haven't considered here. Yesterday we considered narrowband IoT, not access control. Today this one access control only, not the narrowband IoT. General access control. Now I am going to consider access control in narrowband IoT. So if you consider this is narrowband IoT, we have 9 parameters. That is a narrowband IoT. So today I haven't considered narrowband IoT. Just random access. In any system, any wireless communication system, just random access. Say whether it can be Wi-Fi or whether it can be 5G new radio or LTE, any device to establish the connection using preamble. Say here, today, where did I consider the repetition? Today, where I consider repetition, where I consider the random access opportunity, where I consider, I haven't considered anything. Where? Yeah, only these things we have considered. Sorry? 4 parameters only we considered today. So we haven't considered narrowband IoT. Huh? So this one for any wireless network. Yeah. Now I am going to consider narrowband IoT. Yesterday we just considered narrowband IoT. We haven't considered access control. But in practical scenario, we must have both access control. And if you take the narrowband IoT, practically we have to control 9 parameters and other random access control parameters. Like this, yeah. So that's what here, now I am going to consider 14 parameters. 9 plus 4. ACB or backoff factor or distributed queuing. So 9 plus 4, 13 parameters. Distributed queuing, there are two parameters. Distributed queuing, depth and degree. ACB only 1 parameter. Backoff only 1 parameter. Yeah. Depth and degree. Yeah, 4 parameters. So 9 plus 4, 13 parameters. So 13 parameters if you use hybrid access control. If you use only one ACB, 9 plus 1, 10. If you want to use only backoff, 9 plus 1, 10. If you want to use distributed queuing, 9 plus 2, 11. If you want hybrid, so that means the ACB failed, then go to backoff, then go to distributed queuing. Quickly to reduce the energy, if you use that, then we are going to have 13 parameters. So now, we found that when we consider the 13 parameters, so this is the bursty traffic. So here, the 13 parameters decoupled is this one, the hybrid scheme. This is the hybrid scheme. This one is the decoupled one. This one fixed value. This one constant narrowband IoT, only random access here. So that means this green one, only the 9 parameters constant, only changing the 4 parameters. The blue one, 4 parameters constant, only changing the 9 parameters. So in these two, we change all 13 parameters. So the red one, so all 13 parameters changing, but not decoupled. The black one, decoupled and all 13 parameters changing. So from this, what the conclusion is, so by decoupling, so we can predict the load accurately and access control performance better. Huh? What is decoupling? Is say here, so that means you don't need the load prediction. So decoupling means you predict the load first, then you control the parameters using the reinforcement learning. So if you don't have decoupling, you don't have prediction. So just 13 reinforcement learning agents, they dynamically change the parameters. So decoupling is, so prediction and control separate. So if you have the, if you don't decouple it, everything together, prediction, the parameters, everything together, access control parameter, everything together. So the conclusion is, so you have to predict the load for the next time slot is essential to control the parameters. Okay, so now, so this one, so we see the convergence. So when you decouple, it converges quickly because we know that we know that we can accurately predict the load. So then initialization would be better. So if you can because if you take the machine learning, the convergence depends on the initialization. So here, when we have decoupled and when we predict the load, we are initializing the better initialization. So that's what it quickly converges. So now, so if you are interested, so to want to learn, then you can read the papers. Because I haven't included all the details here. If I include all the details, I cannot finish it everything within 10 hours. So if you want to learn, so those who are interested to work in this specific area, you can read. So if you have just general knowledge, so that's what because some students here, many students with the master's degree. So then for them, if I start all the derivations and put everything, they will not be able to understand anything. So that's what I provided the slides at the high level, so the MSc students also they will be able to understand. If you want for your PhD research, you have to read the paper and each line by line you have to understand. Okay, now the next topic. Okay, so now earlier I mentioned about for massive connectivity, we are going to have non-orthogonal multiplexes. Okay, no problem.